In this video, we're going to begin talking about solving systems of equations when we're dealing with two variables. So a system of equations is two, in this case, or more in the future. So two equations considered simultaneously. And the solution, that important solution we're going to be looking for this system of equations in two variables, is the point where two lines intersect. Now, that's not always the situation for the solution, but in most cases, the solution is going to be a single point. So currently, what we're dealing with, all of the problems in this section, we're going to be dealing with two lines. So we'll have two equations, which will be linear right now, and we'll be looking for that point where the two equations intersect, or potentially never intersect, or potentially intersect everywhere. Moving forward, we'll talk about two planes, thinking about a plane as being a flat surface, and finding that line where two planes may intersect. That's not the best drawing. And then, in trig, we begin to talk about, well, where do two curves intersect? So here we have a cubic curve and a line, and there are 3 points of intersection. So there's a lot of expansion on this topic. But again, just for right now, we're going to be looking for the solution for two linear equations. And again, most cases, that's going to be the point where they intersect. So as it says here, a solution of a system of equations in two variables consists of all the ordered pairs that make both equations true simultaneously. So as I've said, we can, and what you will probably see most of the time on your homework, is exactly and only one common point, one solution. And these words in blue, consistent and independent, I don't really focus on that, but you will see that built into your homework. So this is a consistent and independent solution. Now, we could have the situation where we have two parallel lines which never intersect. That's the definition of parallel, which means there are no common points and therefore no solution. This is an independent, a singular solution, but it is considered inconsistent because it doesn't make sense, no solution. And then the third situation you may encounter would be having two identical lines. And there are infinitely many common points on those two lines because they're touching everywhere and they go, they continue in either direction forever. So that would be infinitely many solutions. This is considered a consistent solution because it makes sense. But we call this a dependent solution. And we'll look at an example where we have a situation where the dependent variable, the y value, it depends literally on x. We have to write it a specific way. So we have three methods that we can use to solve a system of equations in two variables. Now, graphing, we're going to do that first, and that's not always accurate because unless you're plotting and you've got all your little crosshairs and you know that those points are ending right on that crosshair, you don't know what the solution is. You can use your graphing calculator to check, but I'm not going to want you to do that on the test. I'm going to want to see work. Okay, so just using your calculator to find the solution isn't going to be adequate. I'm going to be looking for work on your paper. So we will graph to help us understand, but that's not a method we would use on the test. So we're going to focus on, after we do this first example with graphing, we'll focus on learning the substitution and elimination methods, and both will work, and those will be acceptable solving methods for your test in this unit. So let's look at an example where we graph and we find that solution for the system of equations in two variables. Here we have a system of equations. We have two linear equations and they're written together. You may see them occasionally written with a curly brace to keep them together, but we want to understand that we want to solve and we want to find the common point or the common solution a ordered pair, an XY ordered pair that works in both of these equations at the same time. So let's deal with graphing each of these equations. I'll first deal with my first equation. In order to graph it, I want that to be y equals. So I have y equals negative 2x plus 1. Now, my slope here is negative 2, and my b value is 1, so my y-intercept is 0, 1. If I look at graphing this line, I'm going to go to y equals positive 1, and I'm going to draw my y-intercept. So now I need to show my slope of negative 2. Remember, slope of negative 2, that's the same as saying negative 2 over 1. And if we think about that as rise over run, we would rise negative 2. That would take me down 2, and we would run forward 1, taking us to that point right there. And as I look at plotting more of those points along that path, remember we could rise up 2 and run backwards 1, we begin to see a nice line appear on our paper. You notice that all these dots are on the same line. So let's repeat this process for my other line. I'm going to rearrange that. X equals 5 plus y, or x minus 5 equals y. Here my slope is positive 1, and my y-intercept, my b value is negative 5, so my y-intercept is 0, negative 5. So I'll count down 5 units, and then I will travel up 1 over 1. And you'll notice, since I'm plotting all of these points on these little dots or crosshairs, if you will, that we can see exactly that point of intersection or the solution to the system of equations. That ordered pair is at positive 2, negative 3. So 2, negative 3 is the one ordered pair that would give me a true statement in either of these equations. And we can check that. So in my red equation, I've got 2 times 2 minus 3 equals 1, or 4 minus 3 equals 1. That would be a true statement. That means this ordered pair is on that line, as well as 2 minus negative 3 equals 5, or 2 plus 3 equals 5. So this ordered pair is on both of those lines simultaneously. There is one unique, consistent, it makes sense, and independent. It is a singular solution. So that's what we'll be doing in these coming examples, but I really just wanted you to see what this looks like on paper and what that point is that we are finding. As always, email me if you have questions. There are more examples to come.